Welcome to the HasMotion YouTube channel. In today's video, we will be continuing the plug and gait model we started in the plug and gait upper body model tutorial and building the lower body segments necessary to complete the full body model, following the Vicon definition. The lower body model can serve as a standalone model for lower body trials or can be combined with the upper body model to create an entire model. The link to the video describing how to build the corresponding upper body model can be found in the description. You might notice as this tutorial progresses that some of the segments look a little off or unusual. This misalignment is due to errors in the marker placement and the dataset. To see a modified version of this tutorial with updated definitions to account for this error, watch the next video in this series titled Modified Lower Body Model. The link for this video can also be found in the description. This model will consist of the pelvis segment and everything distal to that, including all lower body segments. The marker set used for the static trial consists of 12 markers, 6 for each leg. Vicon defines the origin of the segments at the distal end of the segment, whereas Visual3D defines the origin of the segments at the proximal end of the segment by default. This tutorial chooses to define the origin at the proximal end of the segment as this is more convenient in Visual3D and won't affect the results significantly. This tutorial uses the Visual3D default segment orientation. If you review the Vicon documentation, the segment orientation and colors are different from those in Visual3D. To download the necessary static files for this tutorial, please follow the link in the description to the corresponding wiki page for this tutorial. We'll begin building the model for this by loading the static trial included in the data on the wiki page, which was donated by Vicon. If you're continuing from the upper body model, this step isn't necessary. From the model menu, select Hybrid Model from C3D file. Select the calibration file and apply it to all relevant moving trials. Now we'll start defining our segments by creating important model metrics like height, weight, and joint radii. Click the Subject Data /Metrics button, select Mass, and click Modify Selected Item. Change the value to 75. Next, we'll change the height to 1.76. Now we'll add a new item named Marker Radius and set the value to 0.005. This indicates the radius of each marker on the subject. We'll also add two new items named Left Knee Width and Right Knee Width, each with a value of 0.105. Now that we have our values for left and right knee, we'll also make an item named knee width that is an average of the two widths, defined by the expression left knee width plus right knee width divided by 2. Now we'll do the same for the ankles, creating left and right ankle width, each with a value of 0.07, and a matching ankle width value that averages the two, the same as we did with the knees. Now that we've taken care of the ankle values, we can create a value for the left leg length and define it as either 0.940 or as an expression, which is the distance between the LASI and LANK. Next, we'll do the same for the right leg length and define it the same way. Now, the same as we did for the knee and ankle, create a new metric named leg length and define it as the average of the two. Create a new value named C with the expression 0.115 times leg length minus 0.0153. Now we'll create another value named theta and define it as 28.4 times pi divided by 180. Additionally, create beta and define it as 18 times pi divided by 180. The next metric we'll define is x distance, which we'll define as 0.750 or as 0.1228 times leg length minus 0.04856. Finally, create HJC underscore ML, HJC underscore AP, and HJC underscore AX. These will be defined as C times sine theta minus 0.5 times ACIS distance, X dist minus mark radius times cos beta plus C times cos theta times sine beta, and X dist minus marker radius times sine beta minus C times cos theta times cos beta, respectively. Feel free to pause the video to get those definitions down. Now we can move on to defining our pelvis segment. In the segment name box, type pelvis and select the code definition. Check Use Calibration Targets for tracking, and Apply and close tab. The code of pelvis automatically creates hip joint centers using the Bell and Brand regression equations. The plug and gait model uses the Davis regression equations. In the next steps, we'll create the right hip joint center and left hip joint center using the Davis regression equations. Create a new landmark named RHJC and define using existing segment pelvis. Offset using the follow medial, lateral, anterior, posterior, and axial offsets. Negative HJC ML in the X direction, HJC AP in the Y direction, and HJC underscore AX in the Z direction. Copy and reflect this new landmark to create the left hip joint center. Now we can use our new landmarks to define the thigh segment. We'll define the thigh segment using the proximal joint radius at the right hip joint center and a radius of 0.5 times the distance of the right hip joint center and left hip joint center. The distal joint radius will use a lateral marker at the right knee marker and a radius of 0.5 times the knee width plus marker radius. We'll use an extra target to define the orientation at the RTHI or right thigh marker, and we'll check Use Calibration Targets for tracking and click Build Model and Close tab before proceeding. You should now be able to see your right thigh segment, and we'll copy and reflect this to build the left thigh the same way. We must now create new landmarks for the knee joint centers at the LKJC and RKJC, or left knee joint center and right knee joint center. Create a new landmark named RKJC, defined by the right thigh, and using medial axial offsets of negative 1.0 in the axial direction. Check offset by percent 1.0 and build your landmark. Copy and reflect it for the left knee joint center. We can use this new landmark definition to build the shank segment. Select right shank in the segment name box and click on the Create Segment button. In the right shank tab, enter these values. Define the proximal joint using the RKJC as the joint and the radius as RTH underscore distal underscore radius. Define the distal joint using a lateral marker at the right ankle and a radius of 0.5 times the ankle width plus the marker radius. Use an extra target to define the orientation as a lateral target using the right tibia marker. Check Use Calibration Targets for tracking and build the model. Again, we'll copy and reflect this segment to build the matching left shank. Now that the upper segments of the leg have been built, we can start building our foot segments. Here we will build two foot segments, one being the virtual foot. First, start by adding a new landmark for the right ankle joint center. Click Add New Landmark and enter RAJC. Define using the existing right shank segment and an axial offset of negative 1.0. Check offset by percent 1.0 and build your landmark. Reflect it for the left ankle joint center. Now in the Segments tab, select right foot and we'll define it using a joint center at the RAJC and a radius of the right shank distal radius, and a distal joint center at the right toe marker, again with the radius of the right shank distal radius. Use an extra target to define in the posterior position using the right heel marker. Check Use Calibration Targets for tracking. Build your model, and once again copy and reflect it to build the corresponding left segment. Now we'll build the virtual foot segment, which exists to more closely model the movement and positioning of a real foot relative to the lap. Create a segment named R virtual foot and define the proximal joint center at the right heel marker and a radius of 0.1 meters. The distal joint center will be at the right toe marker with a radius of 0.1 meters, and an extra target in the anterior position at the right ankle joint center will be used. Check Use Calibration Targets for tracking, and click Apply and Build Model. For the virtual foot, we'll modify the segment coordinate system. For the anterior-posterior axis, we'll use positive Z, and for the distal to proximal axis, we'll use negative Y. This segment can also be copied and reflected to make the left virtual foot. Your plug and gait lower body model is now complete. You'll notice that some of the segment orientations look a little bit off. We'll continue by fixing this in the modified lower body tutorial that can be found in the description. Thanks for watching.